Thermal drift is white noise, and at the least significant bit level, and the 6 dB per bit rule of thumb comes from wanting to have the variance of the quantization below the SNR of your signal. So we have to measure these things, right? But that, yeah, yeah. No, that is, I guess I was inarticulate before. The quantization noise is just you just add more bits, and I think that's not fundamentally a problem. But the way most A-to-D converters are built is they have in effect amplifiers inside which do sampling and holding. So you sample it and you hold it, and there's an RC time constant associated with that hold, and you don't want the thing to droop while you're converting it. Maybe that's okay. But there are implicit gains, and if those gains are not matched very carefully, or if there aren't calibration signals routed around the network, and they're in general functions of temperature, and even though the temperature is being exquisitely controlled here, I'd be willing to bet you that Lisa will have to transmit other signals around the network every once in a while just to be convinced that the A-to-D converters are working. Anyway. So the problem here, if you're trying to measure, if you're trying to calculate H, is you need to know the noise and you need to know the signal. And the noise is given by the spectra that I talked about before through the transfer functions. Again, it's the spectrum of the noise times the bandwidth, which is 1 cycle per year by hypothesis in this one measure of sensitivity. And then you've got to divide that by the RMS gravity wave response, and it's conventional to multiply by 5. So I'm going to very quickly show you algorithm, just a cookbook for calculating both the numerator and the denominator here, and then some examples under various conditions. So the cookbook for calculating the denominator, which is the gravity wave signal, is that you pick which TDI comes.
By the gravity wave signal, you mean if you have a sinusoidal gravity wave at some frequency?
Yeah. Yes.
What do you get out in terms of Y? Or?
Yeah, because of the linearity, of course, you get a sinusoid in gives you a sinusoid out, and so excuse me. So the but each of these alpha XP have different definitions, transfer functions. So you just play the sinusoidal gravity wave through the transfer function that you specify, which cancels the clock and the optical bench, the clock, the laser and the optical bench, and then see what the RMS output is given a unit input, for example. And you trace
RMS output for alpha
or for whichever one you want to do, and I'll show you examples of all of them. But you do exactly what you just said. We're going to do sky and polarization averages, and so for you pick random points on the sky. So you've got 2 coordinates for the right ascension-like and declination-like coordinates relative to the array. 2 other numbers specifying the polarization state. So 4 numbers for each point. You then calculate using Hugo's formula the psi i's, which depend upon the spacecraft position and the orientation of the array relative to the gravity wave and the polarization state. From the psi's, you calculate the little y's. There were formulas earlier. Then you just plug them into the transfer function. If it's x, you use the transfer function for x. If it's p, you use the transfer function definition of p. And that then gives you the output you would get had you formed that particular TDI combination. And it's very useful to check this against the long wavelength limit. And this comes to a point that Kip made earlier, and I'll expound upon this. You can get analytical expressions in the limit where the wavelength is large compared to Lisa. You can get analytical expressions, and you can test your codes and find some errors, some class of errors, by requiring that those two agree, being sure that those two agree. And then you just iterate that. You do that for frequency 1, and you do it for n sources. Then you move 1 frequency bin over and do it again. And you build up then the sensitivity curve as a function of Fourier frequency in this way. Actually, this is not the sensitivity curve. First, I'm telling you how to calculate the RMS gravity wave response. I'll tell you about the sensitivity in a second. Let me just digress to say that the long wavelength limits are given in some of the references that I had there. And so, so you remember that the size were proportional to h, and when you play it through the transfer function for each of these things, in the general case of unequal arm lengths, a general triangle, not all the same arm lengths, the RMS gravity wave response is proportional to the second time derivative of h. So you get suppression at low frequencies. Now zeta, as Kip pointed out, has a very special property that if the arm lengths are equal, then zeta cancels to second order, and the first non-zero contribution is at third order. So zeta is in some sense, well, is in that sense insensitive at low frequencies to gravity waves, and I'll show you some plots in just a second. So here is an example of the RMS gravity wave response for alpha as a function of Fourier frequency log. For the nominal equilateral triangle case, what you're seeing here is the fact that at low frequencies it's coming up like f squared because of the long wavelength limit alpha was proportional to h double dot. And as you get to the point where the wavelength of the radiation is comparable to the wavelength to the dimensions of the apparatus, then that's no longer true. And averaged over the sky, you see a response which is roughly constant. For some other combinations, this is combination E, you get the same behavior at low frequencies, f squared, but because of the transfer function due to gravity waves, you get nulls. Now, it happens that these nulls are going to cancel, are going to come at frequencies exactly where the noise also has nulls, and so that the response is going to be okay. But these nulls are real in both the numerator and the denominator of that expression for the sensitivity. So here's what they look like for all of them. So this is RMS gravity wave response for a unit excitation as a function of Fourier frequency log. They're all coming up. Well, not all. All but zeta are coming up like f squared. Zeta is coming up like f cubed. It's strongly suppressed. Here to here is 1 order of magnitude at low frequencies. At high frequencies, as Kip alluded to, the responses are comparable, with the exception of the nulls due to the transfer function for some of the observables. And again, this is just linear algebra. There's nothing tricky going on here. No. Okay, so that was the denominator, the RMS gravity wave response. The numerator, you need to get the noises, and I've talked about that from the pre-phase A, or from measurements. You have an estimate of the spectrum. I like to convert these to the power spectrum of Y, which are all these plots that I've shown you are in terms of delta F over F. You write down the transfer function, and you just Fourier transform a square, and that gives you the spectral modulation. And so that gives you the time domain representation of the noise, and it looks like this. So what's plotted here is the logarithm of the spectral density of the TDI canceled combinations. X is the unequal Michelson, zeta is the symmetrical Sagnac, alpha is the one that I showed earlier, that's the green one, as a function of Fourier frequency. So after you've played all these things, all the noises through the transfer function, and then multiply times the raw noise of the proof mass noise and the shot noise out here, you get spectra which expressed in terms of delta F over F, which look like this. So loosely speaking, here's shot noise with modulation. Loosely speaking, here's proof noise played through the transfer function. So now you have the numerator of what you need for the sensitivity here, and you got the denominator from the previous calculation. So to remind you, we're trying to calculate this. We have the power spectrum of the noise. That's this graph that I showed you. We multiply times the bandwidth, 1 cycle per year, take the square root. That gives us the RMS noise. And using the prescription that I showed you, you can calculate the RMS gravity wave response as a function of frequency. So you have both the numerator and the denominator, and then hence you can calculate the sensitivity, which is the magnitude of the signal averaged over sky and polarization that you have to have in order to get an SNR of 5 at each of those frequencies. So this is it. This is the one that's always published. This is the unequal arm. This is the Michelson on the case where it's equal arm. So what's plotted vertically is the logarithm of strain sensitivity H versus logarithm of Fourier frequency. What's happening here is you're seeing the noises expressed in these ways are constant at low frequencies, and the signal is suppressed, so therefore you require a stronger signal at low frequency to overcome the noise, because the transfer function to gravity waves is not so good at low frequencies. So this is proof mass noise dominated here. Here you're all shot noise dominated. And because shot noise is white phase, which may be the way that you're more used to thinking about them in terms of frequency, you differentiate that and you get f to the +1, and then anyway, it's f to the +2 in this kind of representation. So anyway, it comes up. The phase noise is coming up like this, and these wiggles are all real. Maximum sensitivity about 10 to the -23 at about a few 100-second wave.
So the way people often think about this is the amplitude of a periodic source, which is a binary system, that it could be detected if there's no source confusion.
Exactly.
With a 1-year integration time.
Right. And as Kip alludes to, Strolfini and others have discussed the fact that at low frequencies there's likely to be, almost certainly going to be, a confusing background, and I'm going to talk a little bit about that in a second, about how you might get out of that. That was for the unequal arm Michelson case. Oh, sorry, that was for the Michelson case under the specialization to equal arms. These are the other TDI combinations: alpha, zeta, U, E, and P. They're all about the same at high frequencies, and as Kip pointed out, it's only at low frequencies where zeta is significantly suppressed compared to the others. So it's for frequencies that are, say, 10 of them, roughly speaking, 1 cycle every 100 seconds and lower, that zeta is relatively insensitive. At higher frequencies, they're all comparable. And in fact, this trick can be used. Tom Prince, Shane Larson, and Massimo Tinto are exploiting the fact that there is important signal coming in from the zeta combination at high frequencies to optimally add the signals from the 3 possible interferometers to get better sensitivity.
Now, why is it that alpha has this peculiar behavior so different from the others?
Well, okay, Pete Bender likes to call this one of the Sagnac things for that reason, and he calls this a symmetrical Sagnac. The mathematical reason is if you look at the number of delays which go into the thing, you can put a zero or a suppression of the signal at certain frequency for this peak. So the gravity wave required here is being suppressed a little more than it would have had you offshifted it a little bit in terms of double delays. The X's involve double delays, for example.
So if you shorten the arm length so the floor broadens out, does this alpha still take off from basically the first minimum?
Okay, so the question is, what happens if you shorten the arm length? And this is if you divide by the arm length by 3, it looks like this. And if you divide the arm length by 10, it looks like that. And if you were to make it 3 times longer, sorry, that's nominal. If you were to make it 3 times nominal, it looks like this. There's not for all these combinations, but for the unequal arm Michelson combination, Shane Larson has a very nice tool on the web that you can play the parameters with and play the game. And that would be for the red one here, X. But these others are The qualitative behavior, I think, is not mysterious. It just when you, for example, make the arm length 3 times longer, you're in the long wavelength. You have to go to bigger waves to get in the long wavelength limit. So this just shifts over here. But of course, for constant optics and power, the shot noise goes up, and so this then becomes a sort of it's shifted this way and scrunched a little bit, and then the converse is true as you go to shorter arm lengths. And of course, you don't have to do it for equal arms. This is an example of the Michelson combination for if you were to have a configuration which is isosceles, where these 2 arm lengths were equal to at least the nominal, and this one is not quite twice it. This is the so-called X Michelson interferometer, the one with this is the vertex, and Y and Z, which are that vertex and that vertex, are this one, and the zeta has now, because the arm lengths are not, it's not an equilateral triangle anymore, zeta is coming in as H double dot rather than H triple dot, and so the efficacy of using zeta to measure the noise independently of the gravity wave is somewhat lost. And you can have, I mean, this is sort of fun to do. You can make catalogs of these things. For example, here's PQR, which are other combinations, and they all have, they're not fundamentally different from what I just showed you for X, Y, and Z. The zeta is, of course, zeta. It's now coming in second order, and you get something that has roughly the same sensitivity as X at low frequencies, with details different. Okay, so how might you exploit that information? This, as has now been sort of beaten to death, the different TDI combinations have different couplings to gravity waves. And the symmetrical Sagnac at low frequencies is to some extent insensitive to gravity waves, but contains information about the noise. So the idea then is you look at, say, X, the Michelson combination, simultaneously with zeta to isolate signal plus noise and noise only. And I'll show you some plots in just a second. There's also a sort of a clever idea by Craig Hogan and Pete Bender to take the spectra of X, Y, and Z, not X, Y, and Z themselves, but their spectra, and combine them in such a way as to get at, in a somewhat better way, get at gravitational wave backgrounds. So this is X and zeta. So the idea again is shoot down here where the astrophysics suggests that we're going to be confusion limited. We have zeta, which is insensitive to gravity waves, and X, which is sensitive. And this is a plot from a paper that Massimo Tinto wrote, showing if you were just to take if the only gravity wave sources were confusion limited binaries from the galaxy, and you looked at you formed X of t, you Fourier transform it and square it to get a power spectrum. If there were no signal, you just see this, which is the spectrum of the noise. If there were a gravity wave background, this is sort of the guess as to how that might look. So X would look like this, and back down, because it does see the gravity wave background. And you wouldn't know necessarily whether that was a real gravity wave background or a malfunction of one or more of the proof masses. But zeta would look, if zeta were operating normally, it would look like this, because it would be totally insensitive to that gravitational wave background. It would be orders of magnitude suppressed. So by looking at zeta, you measure the noise independently. Looking at X, you measure signal plus noise. Okay, there are, of course, problems. The actual LISA detector will necessarily have lasers that do not have the same center frequency, and there will also be Doppler shifts. A consequence of that is that the optical bench noise no longer cancels. I'll show you a plot. And noise from the ultrastable oscillators, which are used to count these fringes, now comes in. Now, the bad news is that ultrastable oscillators are only stable at about maybe 1 part in 10 to the 13 for count times of 1,000 seconds. And so this would introduce unacceptably high noise if you did nothing. So there are tricks to do something. I think Ron Hellings and Carsten Dansman have an idea which is further elucidated by Massimo Tinto, Frank Estabrook, and me. And the sort of the bottom line is that by sending extra signals around the network to sort of calibrate out the USO, it'll work. But it now is looking a lot more complicated. It's looking sort of messy. And one consequence is that the optical bench noise, which used to look like this is the noise in the X observable, the unequal arm Michelson. This is proof mass noise and shot noise modulated. In the old days, if they were all same center frequency and no Doppler shifts, this noise canceled exactly. It could be made those are the so-called capital V's, the optical bench noise. Now they don't cancel exactly. They come down to here. They cancel acceptably, but not exactly. And this shows what would happen to the noise if you did nothing with 10 to the minus 13 USO. You'd be totally swamped. So you're either forced to flying a better clock, requiring that the center frequencies be pretty close to the same, minimizing the Doppler shifts, or well, those things. There's a trade-off between those parameters, and if you're forced to a 10 to the minus 13 clock by technology, which may be the case, the clock makers are not optimistic about improving this, then you have to do something. So let me just summarize. LISA can be analyzed in terms of symmetrically in terms of the one-way links. You can take those time links and those time series, those one-way link delta FORFs, offset them and add them in such a way as to cancel the main noise sources or suppress them in the case of time-varying arms. I'm sort of keen on TDI as a framework for system engineering. You can make trade-off studies. If for example, there were some way to radically reduce the Doppler shifts, you could pick orbits that got the Doppler shifts way down, and if you chose to spend money to stabilize the center frequencies of all those lasers, then you might be able to trade that in terms of money against the USO capability. So there's a system engineering aspect to this that I personally am sort of keen on. You can calculate things across the LISA band, not just in one wavelength limit. And it has the applications that I've mentioned are the applications that I showed you. The sensitivities can be exploited to get at the background. You have some robustness against system failures. If you take all the data and you lose 2 links, you've still got an experiment. To some extent, a limited extent, you can design for certain waveforms by taking the signals and taking, for example, alpha minus beta. You can force the sensitivity. You can move the sensitivity curves around to be better at certain frequencies than others. So if you had a specific signal you were looking for, you could play that game. And finally, something I didn't talk about, you can discriminate signals and noises based on the differing transfer functions. If, for example, there were, for example, X, there's an 8-pulse response to gravity waves, but there's a 2-pulse response to, if there were some giant glitch in the proof mass someplace, then you can discriminate that class of non-stationary noise from a gravity wave. And with that, I'm going to quit. Thank you.
So, what is going to be delivered now?
Well, what I would like to have telemetered down is, in the idealized case that I've talked about here, the 6 YIJs and the 6 ZIJs sampled at times that are appropriate for whatever combinations you ultimately want to do. You probably don't have the bandwidth to send everything down. The bandwidth is not a fundamental limitation. It's only 1/3 of an AU away, but the DSN link is something that Bill Faulkner and others worry about. So you don't need to telemeter everything down if you don't want to.
Worry about in what sense?
In terms of data rate, I mean, you have to track the LISA array with the DSN longer than you might otherwise like to. You might want to store the data and only have 2 or 3 tracks a week and just dump it. But I think you in the simple case, you want those 12 time series appropriately sampled at the right times. In the more complicated case, which the final reference in that set of references I gave you at the beginning. There are additional telemetry things that Ron Hellings and Massimo and Frank have identified as necessary to remove the USO.
So appropriately sampled means how often?
I think once a second at the right time tag. So the bandwidth of the signal might only be 1 hertz, but as Bonnie alluded to earlier, you want to nail it at the right time so that when you do the combination, they cancel. The noises cancel.
Now, on LIGO, it's regarded as crucial to have an enormous amount of housekeeping data to make sure everything's functioning properly.
No doubt Lisa will be similar.
And so I presume there will be pressure to telemeter down a lot of that, or do you think you do enough onboard processing that you can reliably identify anything that's not functioning properly?
I unfortunately have had some bad experiences with not having enough telemetry data from spacecraft recently. So I'm in favor of telemetering down more rather than less now. But there are limits to what you can do. So you have to plan ahead, I think.
Well, what are the limits likely to be?
Well, if it's an X-band link between the Earth and the spacecraft, then the numbers, I don't know what I did right there. But for example, the Cassini link, which is an example of a high data rate link, is about 10 to the 5th bits per second. So you can get a lot down, but you have to, probably for reasons of cost, you want to store it and then burst it down rather than continuous tracking. The DSN problem is, in my opinion, it's been raised, but I think it's a solvable problem. You just have to do it, you know.
So 500 kilohertz is sort of the reasonable X-band.
I don't know what I said. I should have said 10 to the 5th, 100 kilobits per second.
100 kilobits.
10 to the 5th is something that can be done, and that's for Cassini from Saturn. We're much closer, but on the other hand, we have smaller dishes and less power, so it might be a reasonable number. I mean, if this is something one can go look up and argue with the telemetry engineers.
Then the issue, I presume, is how much DSN time can the mission afford.
That is an issue, and I'm not well qualified to comment on that. But it's not a fundamental problem. It's just.
And do you assume that you'll really be working at X-band rather than K-band?
I think I'm remembering the baseline right that it's X-band. Ka-band is you can get 60 dB more. You can get much more data down per unit time at Ka-band, but I believe the baseline is X.
Why is that? Is NASA just switching over to Ka-band?
Well, I'm a Ka-band enthusiast, as you may know, but spacecraft managers are very conservative folks in general, and they would like someone else to be number one, I think. And by the time Lisa comes around, there'll be a few number ones. There's no telemetry, for example, on the Cassini Ka-band. It's just used for the Doppler tracking experiments. So the DSN is actually committed, I think, but it's a chicken and egg thing. You have to sort of work up to it, and I think it could well go with Ka-band.
Yeah, with Lisa 8 years off.
Yeah, sure. It's a long time. I don't know when the decisions have to be made, but it's a long time.
So if we don't telemetry down all the Y's and all the Z's, what other options do you have? And
well, you could form
any of the variables. You have to be able to communicate to the spacecraft, presumably. For instance, if you want to form PQ and R, you have to know what's going on the distant spacecraft.
Well, yeah, you do, but you could imagine a situation where you have. And I don't advocate this incidentally, but you could imagine a situation where you know the orbits very well. You have to update to get this 30-meter thing. You'll have to update the. Well, okay, you know the orbits very well, so you could in principle calculate all these things on board. You could calculate X, Y, Z, P, Q, R, alpha, beta, gamma. You could calculate all these things on board and just telemeter down those time series.
Right, but if you Go ahead, Kim.
Do the spacecraft communicate with each other? And then
They-
signal down?
I believe that's the baseline, but in any case, it would be easy to do so because you just modulate the light.
So it's assumed that only one of these spacecraft is transmitting down.
I believe that's the baseline for the thing.
So to compute, say, P, which is beacon mode.
Whichever one, okay.
Okay, yeah. I mean, you're saying that, say, the Vertex spacecraft would transmit its phase readouts to one of the distant
It
spacecraft.
would just transmit. If P is the one where one of them just transmits, it would just transmit. One of the other two would have to get the, and I haven't thought about this in terms of the robustness, in terms of losing links, but the information is all in principle there. I mean, it can be routed around the array to a spacecraft that has a computer on it, and you could just form
But
these
you do
things.
have to route it around.
Oh yeah, sure. You got to keep track, and you have to have a buffer that's maybe, as Bonnie pointed out, order a minute long to initialize the situation. But these are really not difficult problems, I don't think. At least they're not difficult problems. People do this stuff on the ground. The DSN does this stuff on the ground with, operationally.
I mean, just kind of from the viewpoint of doing data analysis, it seems that the maximum information is obtained by having all the Ys.
I think having the Ys,
stored on the ground.
yeah.
So in the future, we can create any signal we want.
yeah. I certainly subscribe to that viewpoint. You do have to, however, though, have the Ys sampled at the right times.
Yeah, that's right.
So there is that issue that you've made an inexorable decision on the computer to sample things at the right time, unless you're going to send down more bits than you might otherwise want to send down. But these are system engineering issues, and I'm sure the system engineers, given a week, I think could come up with great solutions.
Could I give him a week?
Given a day, whatever.
Could I give him a week? How does the sensitivity depend on the direction of the gravitational?
I'm sorry, I couldn't hear the question.
How does the Lisa sensitivity depend on the direction of gravitational wave?
Yeah, well, everything I've showed you was averaged over the sky.
Average.
Right. All the plots that I showed you are averaged on the sky. I don't have plots for specific directions, but so I can't show them to you. But it's just the same prescription. You specify the position of where the gravity wave is coming from, calculate Hugo's psi sub i's, plug it into the noise canceling equations, and that's
Will it be
it.
very different, but different direction?
What I have done, I have not done a lot. What I've done is little bands around the sky because the background may not be isotropic. It may be predominantly due to the galaxy. And yes, it looks a little different, but the ones that I've looked at are not wildly different, at least averaged over a degree. I have not looked at individual sources, however.
In the long wavelength limit, it's just a quadruple around.
Yeah, great, okay, yeah.
So it differs by factor of order 2 from one direction to another.
Yeah, so
In the short wavelength limit, it'll differ a little more.
yeah. One thing that Frank was very interested in for a while was to look at the what you might call the antenna pattern on the sky in the short wavelength limit, and then we changed the frequency by some trivial amount. And of course, the pattern would completely change. It would just go plonk. And it'd just look different. And so then I abandoned that at least because I didn't quite see how to interpret it. It was quite different from frequency to frequency.
Well, sure. Thank you very much.
Thank you.